Yeah, okay. So it's 9 o'clock, so I'll start. So hello everyone. Welcome to Orbit Sessions Part 2. We'll talk about post tracking and shooting on the move. Thank you so much for joining us. If you have any questions during this talk, you can submit them via the Q&A section in this Teams. And yeah, let's just start. Okay, so about us, my name is Jan. 2023 was my first year on the team, and I was in a vision sub team of the programming sub team. And in 2024, last year, and 2025, next year, which is going to be my senior year on the team, I was a part of the robot sub team of the programming sub team.
Hi, I'm Itai. 2023 was my first year in the team. I was in the PC sub team, which is a sub team of software. And last year and next year, when I'm gonna be a senior, I'm working on the robot sub team, which is also a software sub team.
I'm Ido. This was actually my first season. I was in PC as well, and I'm now in the robot software subteam.
So today we'll talk about our post tracker first, everything that goes into merging our position and getting them from our sensors. Next, we'll talk about our 2024 shooting, then about our 2022 shooting, and last but not least, Q&A. So post tracker. Post tracker is what we call, that's the thing that manages our position on the field. Everything is based on our position on the field, almost anything in a code, from shooting to autonomous, intake assist, and really everything. And it is merged, and it merges many sensors. So first, we have our odometry. Odometry, first of all, what is it? Odometry is the post we get from our swerve, from the swerve modules we have from the steering motor and from the drive motor. So the sensors that go into our odometry are first our gyro, which in this year was the pigeon. That's how we get our heading in the robot's yaw. Then we have our absolute encoder. This year we had MA3 type, and we use them only for startup. For each model, we use the absolute encoder. This way we don't have to align our modules to 0 modules every time before we upload our code. And we also have our encoders, both on we use the Talon Effects integrated encoder, both on our steering motor and a drive motor on each model. So we have a bottom up, that's how we do our odometry. And for each model, we calculate the traveled arc between 2 cycles. So in one cycle, the time of that cycle, we'll call it T0. Each model has a velocity. So for each model, we have a V0 velocity in a certain direction. So until T1, which is another timestamp, the robot, this module, has made an advancement in a V0 direction and velocity, but in T1, it already has another velocity, which is V1. So what we do is we calculate the arc between those 2 timestamps. And we do an arc because modeling the movement as a line is less accurate. So our approximation to the model's movement is an arc. And the next thing we do after we calculated the arc for each model, we convert the coordinate system from the module to the robot. So this is our robot. Then for each model, we have the module angle and the module axis. And then we have our robot axis. We call the center of our robot our 0, 0, the middle of our coordinate system. And then we have field axis. So what we do is we rotate everything. We convert the coordinate system for the displacements. Next thing we do is we average the module's displacements to calculate the whole robot's displacement. So each model has its own displacement, and even though they're a little bit different because sometimes we're rotating and some modules do more than others, but they all get the same weight in our whole robot's displacement. And then after we have that displacement in robot coordinate system, we convert it to field CS using our gyro's yaw.
So Jan talked about the odometry, which gets us a pose in a robot pose, but the problem with odometry is that it sometimes drifts. It drifts over time. So we are using the cameras in order to reset the pose when we can see it in every tag. We put the cameras on the robot where it's optimized for best visibility on the main tags. So the ideal would, if we put the camera horizontal, if we get closer to the tag will get out of the frame. So we tilt the camera's mounting a bit in order to achieve more range on the camera and to see more of the tags from farther away and to use all of the range the camera has. And we are putting the cameras centric to the main mechanism or mounted on the moving scoring mechanism, such as 2022's limelight on the turret. And we're putting it there because it's easier to calculate the shooting vector of it, and it gets us better performance because we don't need to calculate the angle between the two mechanisms, the camera and the shooting mechanism. For pose estimations, we have there are two main ways to calculate it. There is the six-axis calculation, which calculates first the robot's displacement, the x offset, y and y offset from the target, and the z offset, and then calculates the yaw, pitch, and roll of the camera. This calculation is done by solved algorithms like solve-PNP or the megatag in Limelight. The problem with it is that it's noisy and it's really sensitive to movements and to any displacement or
Camera's position.
yeah. But our calculation is we calculate the distance of the pitch and the ty that we get from the and the angle from the middle of the frame to the target, and we get the angle towards the target by our gyro and the tx, which is the angle in the x-axis towards the tag. Note that the TX is in the camera's plane, so it's a plane that's at the pitch. It's on a pitch angle from the ground plane, and when we get it, we want to add it to a yaw from the gyro, which is on the ground plane. So we will project the TX onto the ground plane, which will increase it, and then add it to the gyro's yaw and camera yaw offset. We get the distance by getting the target's height, subtracting the camera's height, and then dividing by the tangents of the camera's pitch plus the ty, which is the angle from the middle of the frame to the target. Then we get to the angle to the target, which is the yaw plus the camera's yaw offset, if we have the camera a bit not looking straight ahead, plus the tx after we've projected it onto the ground plane. And we also sometimes take the yaw from the megatag or the photon vision calculation, which are both the six-axis calculation, in order to reset the gyro. And it's done when we are close to the target and we know that the noise and that calculation is minimal and we can trust it. the projecting between planes, it's not really easy to explain, but there is a lot of information out there in the internet, and you can Google it after the session in order to
Understand better.
yeah, but I'll try to explain it a bit here. We get the TX in the camera plane, which is in the picture, the plane 1. But we want to add it to the gyro angle, which is in the ground plane. In the picture, it's plane 2. We need to project the angle from plane 1 onto the ground plane, plane 2, and it is as follows. The tangents of the TX in the ground plane, which is in the plane that we want to, is the tangents of the TX in the camera plane, which is what we get from the limelight or the photon vision calculation, divided by the cosine of the theta, which is the angle between those two planes, which for us, it's the camera's pitch. Now, for our calculation, it's really dependent on the calibration of the camera. So we want to make sure that the calibration is as good as we can do. So first, we are taking the distance from the middle of the robot to the lens of the camera in the X offset and the Y offset. And then we take the distance of the lens from the lens of the camera to the ground in order to get the Z offset. After that, we are getting close to the tag and setting the yaw as the your calculation that the photon vision or the limelight has shown us. And then we are moving to a place where the TX and TY are really approaching zero, like close to zero, both of them, in order to not have the roll affect us. And we change the pitch in order to match the distance that we are measuring from that position, and we are changing it until we see that the distance that we measured and the distance that the calculation is showing us is really similar. And after we found it that is similar, we are rotating the in place and seeing if the robot is moving. It's like it will sometimes, if the roll isn't correct, it will slowly get closer or get a bit farther, and it will change the roll until you see that the robot, when you're rotating it, it isn't moving really. And because every parameter affects the others, we will once again repeat the pitch and the roll until and we will do it a couple of times in order to achieve the max accuracy. Yeah. For smart cropping and family switch, we're using the smart cropping in order to have higher FPS, and this yields better results because we see more tags. And we are doing the two types of crops. The one crop is a big crop with when we don't see a tag in order to search for the tags. But when we detect a tag, as you can see by the GIF down the right, we minimize the crop and focus it on the tag. So we wouldn't miss it, but we would have a higher FPS while tracking it. And for downscale, we have two pipelines this year. One pipeline that had a higher downscale, meaning that we downscaled the image more, and it gave us better FPS. So that pipeline was for the close tag detection, because we wanted higher FPS and we didn't really need the range that the lower downscale gave us. And the other pipeline is lower downscaling, which gives us a better range that we can view the tag from, but it gets us a bit less FPS. So we will crop that pipeline a bit more. Now we get to the game piece camera. First, we have the calculation to the distance to the game piece. This year, the game piece width was greater than the height difference between the game piece and our camera on the rover because we mounted it so low. So we calculating the distance from the width would be more robust than calculating the distance using the height. So the calculation is a bit heuristic. We get the game piece width in pixels that we that the photon vision detection gave us, and we divide it by pixels to rad constant, which is kind of a heuristic constant, which gets the angle of that the game piece takes from the image, and we call that angle theta. And to get the distance, it depended on similar triangles, which is we get it by dividing the game piece diameter in real life by the tangents of the theta that we just calculated. But sometimes we can't use the last formula to calculate the distance to the game piece. It happens when we see that the game piece is cut off at the one of the edges of the frame. So we are using the calculation based off of the height difference, which is a bit less robust, but it's better than just throwing away information that we can get. The calculation that we're doing based off of height is really similar to the one that we were doing for tags, but now that we get the camera height divided by the subtracted, and we subtract from it the game piece height instead of the other way around. And now we take the distance and calculated the pose of the game piece in field coordinate system. We are doing it because the latency of the encoders is better than the latency of the camera. So closing the loop on them is way better than closing the loop on the camera and waiting for the picture of the camera to update after we are changing something, like turning to the game piece. And closing the loop on the encoders results in a smoother motion than closing the loop on the camera, which can result in overshoots. And we calculate the game piece pose in field CS because the target is mostly stationary in field CS. So it's easier to assign IDs to them and to track them. If we miss them for a few frames, but then we come back and see them, we can still save the position of it, and while for the few frames that we missed it. We are doing it by calculating firstly the vector from the camera to the game piece, which the length of the vector is the distance that we calculated earlier, either via the game piece width calculation or the height difference calculation. And the angle of the vector is our robot heading right now, or the plus the camera yaw offset, and the angle to the game piece, which is similar, which we do a similar thing to the April-like calculation, and take the TX and project it onto the ground plane. For the game piece pose in field CS, we take the robot pose, we added the robot to camera that we are doing for the auto camera offset in X and Y, and adding the cam to game piece that we calculated earlier. I'm just going to note that we are doing the same calibration for both our tag cameras and for our game piece cameras in order to because they're doing a similar calculation and we want them both to get a good result because the calculation is so dependent on the calibration. As you can see here, there are a few nodes sometimes on the screen at the same time. You can see the orange node is the node that we chose to assist to or drive to. And the yellow nodes are the nodes that the camera also saw, but we didn't choose to go to them. We also have two squares, one in a lime color and one in an orange color. Both of them are showing the pose estimation from the limelight or the orange pie that was running Photon Vision. You can see that sometimes the robot picture will snap onto one of the squares. That means that the robot has chose the camera's estimations position instead of its own, as the Tsipori will show you.
So this is actually a video from our dashboard. So this is always visible throughout the match. And one other thing is that this is actually a use of our pose tracking, and this the game pieces of course don't help in our pose tracking.
So FOM, or figure of merit, what is it? So we have multiple sensors to find our position, for example, the cameras and the odometry, as said before, and we want to merge them to get the robot position from multiple sensors. So before I explain how we actually did it, I want to note that there are other methods to merge positions from multiple sensors. For example, the Kalman filter, but it was too complicated to actually implement for us and it's a bit difficult. So and this method is actually is pretty good, as you see. So what does figure of merit for a sensor mean? It basically means how much the sensor believes that its position is accurate within some range. So, for example, as you can see in the slide, a FOM of 1 for, let's say, the odometry means that the sensor's position is accurate to within 1 meter. So, of course, yeah. So there's multiple errors that could cause the figure of merit to be higher or lower. For example, the odometry and the gyro drift, but they don't jitter. So over time, the figure of merit will be higher and higher because, again, they drift. So you need to, the error, the accumulated error is bigger. The camera, unlike the odometry and gyro, is absolute, but it does jitter, meaning if the camera, no, sorry, if the robot moves faster or a very high acceleration, then the camera position will be not correct. So the figure of merit will be higher. So how do we actually implement each FOM for each sensor? The odometry, the FOM for the odometry, as I said before, one of the things that we take into account is the drift. So over time, the FOM will be higher, as well as the accumulation of the FOM. There's collision and skidding. So if we collide, our position will be less accurate because the robot thinks it moved, but it collided with something and didn't move. Or skidding, when let's say a wheel is skidding and the robot moves a bit away from its actual position. So and again, as I said before, when the camera is when the robot is moving fast, higher FOM for the camera, and actually, as I said before, when the robot isn't moving fast and the tag is centered in the camera, then of course we give it a lower FOM because the image is not blurry and we can trust it and trust the camera more. We define a variable called robot FOM as the minimum of the sensor FOMs. And how to think about this variable is basically how much the robot is confident in the calculated pose. So as I said before, let's say the camera has a FOM of 1 and the odometry has a FOM of 0.2, then the robot FOM is 0.2, so it's pretty confident, I should say. We know that this method is actually not the most accurate mathematically, but it is simple, and in practice, it's very good for the FRC and works very well. So how do we actually calculate the robot pose? We do a sort of operation called pose merging. So you can see that the formula in the slide. But before that, we first add the displacement of the swerve to the previous robot pose. And that's actually the robot pose in quotation marks, because we take the FOM for the camera, the FOM from the swerve, and other sensors, and basically take a weighted sum, a weighted average of those positions. The coefficients of each pose, as you can see, are 1 over the FOM of each sensor squared. Why squared? Well, it's sort of heuristic, and we saw it produces better results for the position. One more thing to note is when a sensor drifts too much from, sorry, not drifts, like gives garbage information. For example, the camera jitters too much for a certain cycle, then we set its FOM to infinity, and this basically means to ignore the position from that sensor, and you can calculate the position from the other sensors.
So how do we detect skid? First of all, what is skidding? We define skidding as a situation where there is loss of traction between the wheels on a carpet, and there are 2 types of it. And when we're skidding, this means that we cannot trust the odometry. The results from our odometry are really not what is happening in real life, not what the robot is doing. So the 2 types are, first of all, the wheel spins, but the robot doesn't move. So a wheel that's spinning freely, some of the modules. And the second type is skid that's perpendicular to the wheel. This is type that we don't detect. So how do we detect when some wheels are spinning freely? Well, we have, for each model, we have its velocity, which is made out of the rotational part and a translation. So we want to get the translation part. That's the first thing we do. So we subtract all of the rotational parts from each model velocities from the measured velocity, and that's what we get that's how we get the translation. And without the skidding, all of the translation parts of each models should be the same because the robot is moving in one piece. But if it's not the same, then that means that either we're skidding or that the robot is trying to expand itself, which of course isn't a situation that happens. So what we do in order to detect skid is we check the ratio between the model which has the maximum velocity, the highest, that's spinning, the rotating very fast, the ratio between this model and the model which has the minimum translation velocity. And if this ratio is above a certain number, then we call it skidding, a situation when the robot is skidding on the carpet. So what do you do with this information? How do we use it? First of all, we increase the robot's position foam, which, like Ido explained, it'll mean that the cameras will be able to correct our position faster. This is how we actually say that we don't trust our odometry. We just don't give it as much weight as the other sensors that go into our pose. We also ignore the skidding modules when averaging their displacements. As I said before in our in the odometry slides, we said that we are averaging everything and everything gets the same weight. So when we're skidding, the skidding modules, of course, we want to ignore them because they give us false information. And the skidding modules will be the one that are spinning faster because they are the ones who have lost traction with the carpet and are not showing us the real behavior of the robot on the field. By ignoring this, it minimizes the position error due to skidding, and we also increase the position foam. This is how we know not to trust it. And the third thing we do is we also put it into our logger. When we are skidding, this helps us also debug later. For example, if we're in an autonomous path and the robot did not do what we expected it to do, it did not follow the motion path, we know if it was just skidding on a carpet, and that was the reason. So another thing we have is collision detection, which also affects our pose. How do we detect it? When we collide into something, there will be a very big difference between our wanted acceleration, which has its limits, and we know what it is, and our actual acceleration, because when we collide into something, we just stop and we do not continue our wanted movement. So we use our RoboRio integrated accelerometer. We get the information from that, and we consider a spike over 2G a collision. Yeah, so that's how we know when we have collided with something on the field. And what we do with this information is, well, we temporarily disable the acceleration limits. This is to allow our driver to continue its driving freely, because if not, the robot would want to continue its movement the way it was, and it would drive really slow. And we also increase our robot position foam, just like the skidding. So this is from our logger. You can see everything, the whole PoseTracker, everything going together. The white is, this is from an autonomous. The white is the path the robot is trying to follow. The blue and the orange are what the robot thinks it's doing. Orange is when we have a note. And the green and the purple are the positions from the camera. And orange is where we think there's a note. So that's everything coming together. Yeah, so you can see all the notes and well, there's like an orange part over here. I hope you can see my mouse. That's not a note, that's when we are shooting. Yeah. So that was it for the PoseTracker part. We still have 2024 shooting and 2022 shooting. If there are now, we'll answer any questions from the Q&A up until now.
There are any questions?
Are there any questions? You haven't answered yet?
Do you determine the form weights to work model separately, or based on whether it is skidded?
No, it's a singular form for the entire swerve. Again, that you calculate from the skid, the collision, and the drift over time.
Okay.
Şimdi show latency الدول مثلا ممكن خلاص يعني تخشبين بlatency الدول
Do we take into account camera latency? Yes, we do.
Yeah,
Okay.
Okay.
So the next part is going to be the 2024 shooting algorithm. Firstly, the aerodynamics of the node. We showed at the start of the season that the node is too unstable to actually model correctly. You can see at the right the aerodynamics of the node. We saw it in an article at the start of the season, and We also figured that it was difficult to find the nose to drag and lift coefficients. And as you will see in a bit at the 2022 part, we didn't calculate those by ourselves at the simulation. The note exit this year, as opposed to 2022 shooting, the note's path, optimal path, is as close to a straight line as possible in order to get more room for error. This means that we want to shoot it as close to an ideal parabola as we can. So higher shooting velocity means the shot will be probably better. And for the shooting velocity this year, we used a heuristic function that from a certain distance, below a certain distance, it will give the mean velocity, and above a certain distance, it will give the max velocity. And in between them, we are doing just linear interpolation between those 2 points. So we wanted to give our shooting enough power in order to make the shot, but we didn't want to overshoot everything because we saw that sometimes the note will just fly back out from the speaker. So we wanted to minimize those misses. For our shot calculation, after we got the velocity from the heuristic graph that I showed you earlier, we are using that velocity in order to get the angle that we need our robot's shooter arm to move to. You can see the calculation here. It is we've got to it by ourselves at the start of the season because from the ballistic shots calculation from physics, and it was really fun to do. And that's another reason we are using a physics model. And after we get the angle of the shooter, we are calculating a 3D vector that will graph.
Feed our subsystems.
Yeah, we'll feed the subsystems, and it will be as close to the reality as we can. So we do the yaw based on the vector, which is the vector is the target pose minus the robot pose. By the way, we are not shooting to the target. We set a constant in our code that is the target's position, and we are shooting to it instead of the tag. So we're shooting based off the robot's position and not based on a camera. And after we subtract the target's pose xy and the robot's pose xy, we take the angle of it, and that's the yaw that we first put into the vector. The pitch is the formula we get from the formula that is at the start of the slide. And we set the x to the target's position minus our robot's position, and we take the length of the this vector, its norm. And the magnitude of the 3D vector is based on the heuristic graph that I showed you earlier of the velocity of the wanted velocity for the wheels. We take the vector that is made out of the yaw from the angle to the target, the pitch based on the angle, the shooter's angle, and the magnitude that is the shooter's wheels, and subtract the robot's velocity from it in 2D. we set the z part of the robot's velocity to 0 in order to not affect the this part. And that's how we are shooting on the move this year. To execute the shot, we take the yaw of the 3D vector after we subtract the robot's velocity and rotate our robot towards that angle. And we send a control a request for our shooter arm in order to move to the 3D vector that after we subtracted the robot's velocities to its pitch. And we are asking the wheels to go to the vectors, the shooting vectors norm, and follow this, the velocity to be the norm, the 3D vector. For the shooting tolerances, we are using we are making sure that each subsystem will meet the tolerance constraints until we are shooting in order to shoot. And also another thing that we include, because we are shooting off of the robot's position, is we need to make sure that the robot's form is low. Because if the form is high, we are not sure in our position, and we can be even a meter off if we got bumped in the middle, or skidded, or haven't reset our position for a while. And if the form is high, we don't call the rotate function because we don't want to. It also indicates the driver that he needs to see a tag in order to shoot now. And we check the tolerances of each subsystem in meters at the target. By how many meters we allow them to miss, which is not necessarily in subsystem unit. An example for this year is the robot's yaw, the rotate to which we use the rotate to function to correct. As you can see at the bottom right part of the slide, we have a 10 centimeters tolerance for the shot. And if we are at the distance of 1 meter, we get the angle between both the vector form pose to each part of the end of the tolerance, and the angle between those two vectors will be our angle tolerance. How many radians we allow the aim to miss by. But if we are further, you see that the angle that the tolerance gets is smaller. So when we are putting more constraints on when we are shooting the node, yeah, in order to minimize the misses that we have. And by doing the tolerance with the centimeters or meters, when the robot is closer, we allow him to have a bigger constraint, and meaning that it will shoot way faster than it was if it was farther away and had a lower, smaller constraint. Some notes for the shot calculation is that we don't aim at the with the camera's image, both because of the latency that the camera's image has, and that our pose estimation is really good. We aim at the coordinates of the target, meaning that we can sometimes even shoot a note without seeing the speaker's tag. Meaning the shot is relying on the robot's pose, which is this is why we need the PoseTracker so much. The camera is used for adjusting the robot's pose when it has relevant information, such as seeing the speaker's tag when it's close to it and can reset its position of it. And I said earlier, but shots can be executed also without seeing tags based on the PoseTracker. This is why it's really key feature in our code. And you can see in District 1 that there was a defender against us with a flag that blocked the our low camera. And in District 1, we after District 1, we saw that the calibration on our camera wasn't really that good, and we didn't really allow it to. It didn't really allow us to reset our position on the on our course tag that was when we get to our wing. So after we saw that the flag was a viable defense, we worked on fixing that and making sure that we can reset our position off of that tag, of the course tag, before getting into the wing. So you can see in the DCMP that we are just getting into the wing and shooting just when the subsystems are get into place, even if we don't reset our position. So that's it for the 2024 shooting. If there are any questions. Okay.
No, okay.
2022.
And move to 2022.
2022 shooting on the move. Well, actually, one of the things our team is famous for actually is the simulation we made in the season, and we'll show you a bit on how it works and how maybe you could make one in the future season. So first of all, the standard approach. The standard approach for things like this is interpolation. So you measure from a few distances, you search for the optimal shooting parameters for each of those distances from the target, and basically you shoot. For other distances, between the distances that you measured, you interpolate linearly or some other interpolation. It's up to you. When you want to account for the robot's velocity, of course, you want to shoot on the move. There's two approaches that we took into account. First of all, the shooter from our year, which is from this year, from 2024. As Nauman said before, we subtract the current robot's velocity vector from the static shooting vector. Actually, instead of, never mind. We take the static shooting vector that we calculated and subtract the velocity vector of the robot. So that's this new vector to the shooter velocity vector that you need to shoot. Another optional concept that might work will be to calculate a static shot for a future position, meaning you know where you are now and you know your velocity. So you can find where you'll be in, let's say, 1 second, and basically take the static shot of that position in 1 second, which it's practically the same solution. So why did we need a simulation? So as I said before, in the static case, it's pretty much the same. I mean, you take a few distances, you find the shooting parameters, and then you interpolate. So why did we need? Well, when you use spin, specifically the C shooter, because the C shooter, in the C shooter, the spin is actually proportional to the exit velocity, not the exit velocity, the shooter velocity. So when you shoot faster, it causes the ball to have more spin. So when, as you can see in this picture over here, when you subtract the velocity of the robot, the VR, let's say it's moving right, and you want to shoot to the target, you subtract and you get this V out vector. But what happens? The V out vector has a higher magnitude than the V out static vector. So the shooter velocity is much faster, meaning, again, more spin. So this changes the trajectory. Why? Because as we'll see in a moment, there's forces that rise from spin that cause the trajectory to change from static trajectory. So for every distance from the target and each velocity, you get a different ball trajectory for each velocity. This is unlike the case that you don't have spin, and basically for each distance there'll be one velocity and angle. So that's the difference.
Note that if you had a way to set the omega or the spin to be constant, you can use the way of subtracting vectors in order to achieve the shooting on the move. But for our C shooter, we didn't have that option, so we needed the simulation.
Yeah, so as you said before, you can fix the spin, but in that season we didn't have that option. So as you can see, the balls from the 2022 season had a few forces that acted on them. First,
Well, first we have the gravity, which always goes down. Oh, go ahead. Okay.
So, yes, sorry, someone said something. Anyway, the gravity is a force that always acts down. So you need to, of course, this is the force that causes the trajectory to be parabolic, and you need to always account for gravity. Other than gravity, there's air drag and something called the Magnus force. So air drag works in the opposite direction of the velocity, and as you can see in the picture, yeah. So your air drag. This is its equation. It's a very one thing that you have to note is that all the equations and the physics and the math for the shooting of the game piece this season, we actually found from a research paper that someone did regarding shooting tennis balls. And of course, in that season, the game piece was very much like a tennis ball, and so we could use basically the same equations without much change to the coefficients. So as you can see, the formula, it's the drag force equals half the air density times the velocity of the ball squared times the drag coefficient times the surface area of the ball. Again, we'll explain in a minute how you use them. So the Magnus effect, for anyone that wants to know more regarding this effect and study this more deeply, there's actually a video by Vertasim that we suggest to watch about it. So yeah, but as you can see, in a spinning ball, the Magnus effect basically pulls the ball in the perpendicular direction to the plane of spin. I'll see in the next slide. So because the Magnus force acts in the perpendicular direction of the spinning plane, you take the cross product. So anyone that doesn't know what the cross product is, it basically gives the vector that is adjacent to both the vectors in the product, and that's why it appears here. Again, this formula we didn't derive it ourselves. We took it from that research paper that I said before. One thing to note, I forgot to say, is that all these formulas we don't calculate them in real time, because of course air density and the surface area of the ball and the drag and lift coefficients are actually constant in regards to the shot we're making, because it's the same ball and it's the same air. It doesn't really matter. And yeah.
So using this all, accounting for all these forces, how do we actually find a trajectory which we're going to shoot the ball? So we calculate those trajectories from this physics models, but there are infinite trajectories for each robot distance, and velocity, of course, that can hit the target, because when we change our velocity, our shooter velocity, the angle will change accordingly, and we'll just have more spin or less spin. So here you can see on the graph that there are many trajectories, and they would all hit the target. So what we do is we calculate for a range of reasonable velocities. We just calculate many trajectories, but now we have to choose the best one. So how do you do that? So for choosing the best trajectory, we assign a cost value to each trajectory. We would want to shoot the trajectory which has the most chance of getting in the target and also not bouncing out. So what we do is for each trajectory, we assign robustness, which is the Schroth insensitivity to minor deviations in our shooting angle and exit velocity and all of the parameters that go into it. So if this robustness value would be 0, that would mean that we are not sensitive at all, which is of course never the case because we are sensitive. But if the shot would be more robust, it would mean that this would be minimal. So how we calculate that, we take the partial derivatives. We have our distance error and our exit velocity and our shot angle, and for all these parameters we do what will go in even though we are that will go in even if we have small minor deviations. But apart from this robustness, we also have the height, which we are also accounting for, because we would prefer lower trajectories, because higher trajectories, the ball would have more velocity getting into the target and it might bounce out. And we, of course, do not want that. So we would prefer lower trajectories, but with this robustness, the lowest trajectory is also not our best trajectory. So the cost for each trajectory, for each one that we have calculated, for each robot velocity and robot distance, we have calculated all those many trajectories based on shooter velocities. We have assigned cost values to each of them, and then we take the minimum of those costs, and we select the actual trajectory that we're going to use in a robot is the one with the lowest cost. So the one that is the least sensitive and has the best chance of really getting scored into the target. So this whole simulation, that's what it runs, and the output of it is what we actually get. So this simulation, of course, does not run on the robot because it would be too much. And it won't be efficient to do that real time. But the output of this simulation is we get 2 3D matrices, one for the shooter pitch for each robot distance and velocity, and one for the shooter velocity for each pair of robots distance and velocity. So all those 2 matrices for everything that we have calculated, we put them into an Excel and we interpolate those values, all those trajectories that we have gotten. So we interpolate them in an Excel and we calculate a 30-degree polynomial for the shooter velocity and for the shooter angle, which will then feed into a robot, and that's what will actually run on the robot in real time. So we have a function of distance and robot velocity, which is what we also sent into the simulation. And as I just said, we get the 2 polynomials for the shooting vel and the angle. And we limit this function to a 3rd degree in order to prevent overfitting. If we would have chosen a much higher degree, then we'll have overfitting, which is of course not something that we want. So you can see in this graph 4-dimension graph. We have our robot velocity and our distance and our angle, and the color is the wheel's velocity. So you can see that, for example, when we're 4 meters away from the target and we're standing, we'll have a much lower velocity than if we're 4 meters from the target and our velocity is minus 4 meters per second. So yeah, everything just changes the parameters for our trajectory. So in real time on the robot, what's happening? We ran our simulation of the robot. We put everything into an Excel. And from those functions, that's what we feed into our robot. So we create, just like in 2024, we did that once before in 2022, we created a 3D vector to feed into our subsystems of the shot exit velocity based on the simulation. We feed the robot's velocity, radial to the target, and distance to the target to the 3D polynomials to get the shooting pitch and shooting wheel's velocity. That's what the simulation does. So the simulation takes care of the radial velocity. And the yaw is based on the vector, just like in 2024, of our position. That's also when we use our PoseTracker, also just for the distance. Our target minus the robot pose to know which angle we need to turn to. So we should, well, we've already accounted for the radial velocity, but we still have the tangential vel, which is also part of our whole robot's velocity. So we subtract that vector from our 3D vector, and this is how we are able to shoot on a move. So now we have this 3D vector, and we just feed everything into our subsystems, to our hood angle, to our shooter wheels. That's the norm of that vector, and our target angle is the yaw minus the robot heading, because we want to just rotate our drivetrain. And the amazing thing is that this whole thing just worked on the first try. We ran our simulation and we put it on the robot, and all the shots went in. So that was really cool. So you can see here this video, so also at the beginning, that's from our reveal, and it's only like 3.5 weeks into the season, which is amazing that everything just worked and all the shots are getting in even though we're moving. So that was basically it. So a summary of what we talked about today. We described the 3 main building blocks of our software, which are, of course, the PoseTracker, which is the basis of all robots operation in autonomous and in teleop. We really do everything based on that, based on either our actual position, like in shooting, or for our assist, for our intake assist, because everything is calculated in field coordinate systems, and we need our position to do that. And also we use also just our FOM, our confidence in our pose. So everything is really based on that. That's why it's so important. And also 2 ways of calculating things for shooting on the move, for non-spin shooters like in 2024, and for C shooters with changing spin like in 2022. And of course, needless to say that all algorithm and math concepts are written by the team students. 2022, the students back then, 2024, it was us. And that's why we also used those solutions that we were able to understand with our knowledge as just high school students who learn. And that's also why we don't use very complicated stuff like Kalman filter. We just do good heuristics that solve the problems we face, and we just try to simplify everything to our knowledge and our abilities. So thank you all for listening. We hope you learned something and that you enjoyed it. Yeah, so we have now 2 questions that were submitted in the forums in Chief Delphi that we haven't answered yet, and maybe we'll have more. I don't know. Yeah, okay, we'll have more.
So firstly, what cameras do you use? What processors is it on?
So we kind of already answered that, but
Yeah, we're using a limelight for the one limelight for the tag detecting, and one camera, another camera on the bottom vision with orange pi 5 for and also tag detecting, and another camera also in photon vision for game piece detection, and also on the Orange Pi 5. Well, we only have one Orange Pi 5 and one limelight on the robot. What's your favorite April tag camera system? Opinions on photon vision versus limelight for 3D April tag tracking.
So for favorite April tag camera system, I wouldn't say we have a favorite because we do have both. They both have their pros and cons. We find that Limelight might be easier. We really like the different options it has, like cropping and stuff like that, which Photon Vision doesn't have yet. But Photon Vision is cheaper, and they're both Photon Vision. You have one coprocessor, you can have two cameras, so they both have their pros and cons. We have both of them.
Yeah, but the Limelight software feels a bit more polished, and it's easier for the user to actually use. So we usually prefer that, but we also like the Photon Vision co-processing. And for the 3D Maple tag tracking for both of them, we are using the 3D April target tracking for only resetting of the year of the robot. We when we first made the calculation of our calculation from the distance and the angle to the target, we checked it checked the difference between our calculation and the 3D pose estimation the Limelight gave us. And we saw that our calculation was much more robust and didn't jitter and wasn't really sensitive to it.
It wasn't as sensitive as
Yeah.
theirs.
And it didn't flick between a couple of points on an arc sometimes. And so we would recommend if you can to remake our algorithm, but if you cannot, both of the algorithms are pretty good at pose estimations.
Okay, so
The
question שאלות, איך אנחנו מכשירים תלמידים פרצים?
So the question was, how do we
train.
train new students on the team? So I'm practically a new student, as you can see. Basically, it's different for each student. That's what's been said. For me, basically, you read previous robot codes from other seasons, and basically understand things that were done in the season. Like for example, this slide, this session that we that was made. I also helped making it, and in that way, I also learned some of the things that you need to know to be able to work on these. Oh, and coding, so that's also important. Forgot about French, Charlie. In the start of each year, the sophomores teach the new students. So
the seniors teach sophomores.
Just the sophomores basically coding concepts and how to go about this entire thing that's called coding. So yeah.
שואלים אנחנו יושבים בג'אבו, אז משהו תוכל להגיד לנו, את כל שאר התוכנות של האפליקציה.
What? Okay, so for our robot code we use Java, and then for the applications we use Flutter, so Dart for most of them.
Actually, the simulation was written in Go.
Oh yeah.
And the dashboard's backend is written in Rust, I think.
Now,
So
Oh, really?
עכשיו,
אוקיי.
two עשינו אז.
אוקיי.
אני חושב במערכות הסינכרניות בפוסט-טראקר.
No. Okay. Sorry. Do we use asynchronous systems in our post tracking? No, we run everything on just the 20 millisecond cycles, just the normal robot periodic cycles.
אני חושב שבאיזושהי תוכנה פומבית כמו פאת'פלנר בג'ינרות של...
So for autonomous, we have our own Pathfinder. So we don't use Pathfinder and we don't use Choreo or anything like that.
But the our path planner is really similar to Courier or to the public path planner, but we just made it we made it more custom to our own robot and to implement some features that are unique to our robot.
And also it's also fun to just make these. So
He also asked about the drive to function.
okay, a question about the drive-to function. So we actually talked a little bit more about that in the previous session. So you can watch that on YouTube. It's uploaded there. You can just look it up, or there's a link in the Chief Delphi. But basically, it's just calculated on the fly, also based on our position. We just drive to just yeah. It's hard to explain. Sorry. Yeah. So we do. It's more than just drive to just have a velocity in a certain direction. We do something pretty with the velocity, like this trapezoid.
Trapezoid and the acceleration. It's similar to the Phoenix motion magic. Yeah. Back control, but we are doing it on the robot's distance from the wanted position.
Yeah.
It's also based on the PoseTracker. You can see how reliant we are on the PoseTracker. It really mushes everything together and makes everything work. You can get more information, as they said, in the other session that we have uploaded to YouTube, as we are going to upload this session to Orbital.
Okay.
למה לא בודקים את האנקודר האבסולוטי בסביבה כל כמה זמן? עכשיו זה יהיה השאלה פעם.
כן, אני
Why do you don't use it?
Okay. Why do we not? Why don't we use the absolute encoder during the match? For the swerve heading, yeah. We use them. We said at the beginning we use them only for startup, just because we don't need it. Yeah, we have. Yeah, the Falcon encoder is accurate enough. It doesn't drift, so we can use that just throughout the match. We do need the absolute encoders because otherwise we'll start the modules not aligned and we won't be able to drive. But we don't need to use that during the match.
Someone also asked us why on Einstein we put the
Oh yeah.
the wheels at the 0. It was because the encoders didn't. We had some issues in the connections of the encoders, so we wanted to make sure that the encoder is that we get
The right movement.
Yeah, and we're not just drifting in some weird way that caused by one model that is not aligned with the others.
אחד זה איך בונים הקודים בקומנד בייס, אפשר להגיד שדיברנו פעם שעברה.
So a question whether we're command based or time based. We're time based, and that is also something we talked about in our last session. Basically, it's just a few years ago when we switched from LabVIEW to Java. That's what was recommended by WPI, and we just went with it, and we're just stuck with it because it's convenient for us. We don't really find a good enough reason to switch to command.
האחרונה, מספרי אלמוג,
Okay, last question. Who is Omri Almog? He was he was on a team in 2022. He was on a software team. Great man. Yeah, so this is it. Thank you all very much for listening, for being here, for joining us. And yeah, that's it.
Yeah,
Um,
thanks.
Thank you.
thank you
for being
everyone
here.
for joining
Yes,
us.
this is what we saw.
Goodbye.
Okay, have
Sure.
you
And me.
and me.